So now that we know the shapes of our logarithmic functions, let's talk about transforming the graphs, all right? Here I have the graph of y equals the natural log of x. All of the exact same transformation rules that we learned back in chapter 1.7, those still apply to these functions. The same ones that we practiced in the last section of the chapter with our exponential functions. So what is the graph of y equals the natural log of negative x going to look like? Well, recall that throwing a negative constant multiple in front of the x inside of the parent function results in a reflection in the y-axis. When I take this graph and I reflect it over the y-axis, here is my new shape. Notice I still have a vertical asymptote here at x equals 0. However, my x-intercept is now at -1, 0. All right, let's try another transformation. Again, here I have y equals ln of x. I can consider this my parent function, the most simple form of a natural logarithmic function. What is the graph of y equals negative ln of x going to do? Well, here I have added a negative constant multiple in front of the parent function. Negative constant multiples in front of the parent function, that is going to reflect my graph in the x-axis, a reflection in the x-axis. And when I reflect this graph over the x-axis, notice what happens. Okay, my vertical asymptote is still located at x equals 0. My x-intercept is still at 1, 0. But now instead of my y values being increasing, my function is decreasing. There we have y equals negative ln x. Let's look at a couple others. All right, y equals ln x plus 5. Here I am adding 5 inside of the parent function. Notice that when we add or subtract a constant inside of the parent function, that is going to give us a horizontal shift. And in this case, it is going to shift all of our points 5 units to the left. Notice because this is a plus 5, it is going to shift to the left 5 units. Now, what does that do to my graph? Well, this vertical asymptote that was at x equals 0 is going to shift as well. Where is it going to shift to? X equals -5. And my x-intercept that was at 1 is going to shift to -4. And there we have the new shape of our graph. All right, y equals ln of x again, same parent function. Here I have y equals ln x plus 4. Now notice the difference here. This plus 4 is outside of the parent function. It is not inside parentheses, inside of the log, like we saw in this last example. When we add a constant outside of our parent function, that gives us a vertical shift. And in this case, all of the points of our graph are going to shift up 4 units. Notice that shifting the graph up 4 units doesn't change my vertical asymptote at all. Okay, it's still going to be located at x equals 0, but this x-intercept that was at 0, 1, that was at 1, 0, is going to move to 1, 4. Everything gets shifted up 4 units. All right, same parent function, y equals ln of x. What is the graph of y equals 2 ln of x going to do? Well, having a constant multiple in front of the parent function whose absolute value is greater than 1, that generates a vertical stretch. This is a vertical stretch by a factor of 2 in this case. All of the y values of my parent function are going to get multiplied by 2. Notice this y value that was at 1 will go to 2. This y value that was at 2 will go to 4. This y value here that was at -1, that's going to go to -2. Each of the y values gets multiplied by 2. All right, y equals ln of x. What about the graph of y equals 1/2 ln of x? Well, again, I have a constant multiple in front of the parent function. However, this time, the absolute value of that constant multiple is between 0 and 1. And if it's between 0 and 1, that means that we have a vertical shrink. Each of the y values is going to get multiplied by 1/2. So this y value that was at 1 is going to move to 1/2. This y value that was at 2 is going to move to 1. Similarly, this y value that was at -1, I multiply it by 1/2, that brings me to -1/2. Right? All the y values get squished towards the x-axis with a vertical shrink. All right, 2 more transformations. Here I have y equals the natural log of 1/2 x. If I have this 1/2 constant multiple inside of the parent function, that is going to give us a horizontal stretch. Remember, anytime you have something happening inside of the parent function, it's going to be horizontal. In this case, a horizontal stretch. We are going to take every single one of our x coordinates, recall that horizontal scalings affect the x coordinates, and we divide it by 1/2. And dividing by 1/2 is the same as multiplying by 2. So every one of these x coordinates gets multiplied by 2. Notice the one that's here at 1 is going to move to 2. The one that's at 2 is going to move to 4. The one that's at 3 is going to move to 6, and so on. What about the graph of y equals ln of 2x? Well, we have this constant multiple inside of the parent function in front of the x, whose absolute value is greater than 1. That gives us a horizontal shrink. Again, horizontal scalings affect the x-coordinates, and in this case, I'm going to take each x-coordinate of the parent function and divide it by 2. All right, so this x-coordinate that was at 1 is going to move to 1/2. This x value that was at 2 is going to move to 1. This one that was at 4 is going to move to 2. And this one that was at 6 is going to move to 3. We divide all of them by 2. And there we have the shape of our new graph. All right, so all of the scalings, shifts that we talked about, and reflections still apply to our logarithmic functions. All right, so when you guys go to sketch, remember, scale first, reflect, and then shift. Let's cover a couple examples. Use the graph of f of x to describe the transformations that yield the graph of g of x. Sketch the graph of g of x and label any asymptotes. Determine the domain and the range. So here is our function f of x, and you can consider this the parent function. This is the most simple form of a logarithmic function with a base of 10. Yes, remember, this is a common log. If there is no base written, we're talking about log base 10. All right, so what is different in our function g of x? Well, the first thing that jumps out is this negative constant multiple in front of the parent function. Negative constant multiples in front of the parent function give us a reflection in the x-axis. Next, we have this 2 constant multiple in front. The 2 is responsible for a vertical stretch. That's going to multiply all my y values by 2. All right, so the negative here is responsible for the reflection. The 2 is responsible for the vertical stretch. And now I also have a -2 that I'm subtracting outside of the parent function. That is a vertical shift down 2 units. So now we can begin to sketch our graph. Remember, start with scalings, then reflect, and then shift. All right, here is the shape of our parent function f of x equals log of x. And again, remember with your sketches, I'm not asking for them to be perfect. You just have to have the correct general shape and at least one correct point here. So let's see if we can't figure these out. Also, make sure your asymptotes are in the right spot as well. Okay, what do we want to do first? Well, we want to do our scalings first. We have a vertical stretch by 2. That means every single y value is going to be multiplied by 2. All right, now in terms of your sketches, does it have to be exact? No, we just want the general idea. All right, here I've multiplied each y value by 2. Notice that our x-intercept doesn't move at all because the y value here is 0. And if I multiply 0 by 2, well, I still end up with 0. Okay, next we want to reflect. We have a reflection in the x-axis. Reflecting this graph over the x-axis gives us this new shape. All right, and finally, we want to shift our graph down 2 units. Shifting the graph down 2 units brings us to our final graph of g of x. All right, and notice that this point that was at 1, 0 is now at 1 comma negative 2. All right, so where is my vertical asymptote? Well, the vertical asymptote did not move at all. The only thing that's going to change a vertical asymptote for a logarithmic function is if you have horizontal shifts left and right. Okay? If you don't have any horizontal shifts, your vertical asymptote is still going to be at x equals 0. All right, there is our vertical asymptote. So, what is the domain of our function? Well, it's going to be all values of x that are greater than 0. So we have 0, comma, infinity. And our range, well, as I said before, the range of any logarithmic function, no matter how you transform it, is always going to be all real numbers. All right, let's try one more. Use the graph of f of x to describe the transformations that yield the graph of g of x. Sketch the graph of g, label any asymptotes, and determine the domain and the range. So again, here we have our parent function, ln of x, and what is different. Now, one thing to make note of, as I've said before in the past, if you have constant multiples in front of the x inside of the parent function and horizontal shifts occurring at the same time, factor out that constant multiple from each term. In other words, if I factor out a negative 2 from both of these terms inside of the parentheses, I get the natural log of negative 2 times the quantity x minus 2. The reason we want to factor out that constant multiple from each term is so that we can clearly identify what direction and how far our horizontal shift is going to be. All right, so let's take a look. What is different here compared to our parent function? The first thing that we notice is this negative constant multiple inside of the parent function. And negative constant multiples inside of the parent function, those generate a reflection in the y-axis. Now, we also have this 2 constant multiple inside of the parent function. That 2, because it is inside the parent function, it's going to be horizontal, and in this case, a horizontal shrink. Remember, if the absolute value of that constant multiple inside of the parent function is greater than 1, it will be a horizontal shrink. And finally, we have a minus 2 here. That means we have a horizontal shift to the right 2 units. Now that we have identified all of our transformations, we can sketch our graph. Always a good idea to start with the shape of the parent function, okay? And you guys should know the general shape of every logarithmic function by now. Okay, we have a vertical asymptote at x equals 0 and an x-intercept at 1 comma 0. First thing we want to do is scale. In this case, we have a horizontal shrink. We'll take every single one of our x-coordinates and divide it by 2. There we go. We took every x-coordinate and we divided it by 2. Again, not too concerned that you have shown scalings exactly on your sketches, all right, but you do need to make sure that you specify that they are occurring. Next, we want to reflect the graph. In this case, we have a reflection in the y-axis. All right, we're going to reflect our graph over the y-axis now. All right, and finally, we need to shift our graph to the right 2 units. And in doing so, notice what will happen to our vertical asymptote that was at x equals 0. Okay, that vertical asymptote is going to follow any horizontal shift. In this case, our new vertical asymptote is going to be at x is equal to 2. And also notice, let's follow some of our points here. Here we had this point that was at negative 1/2 comma 0. Well, when I move it to the right 2 units, that is going to bring me to 1.5 comma 0. All right, and as we said, there is our vertical asymptote at x is equal to 2. And there we have the shape of our graph. Now, what about our domain? Well, because we reflected this graph in the y-axis, our domain is going to change, right? Our domain is going to be values of x from negative infinity to 2. And our range, As we said, for every single logarithmic function, no matter how you transform it, what you do to it, the range is always going to be all real numbers. All right, and so there you have sketches of logarithmic functions. One thing to make note of, the range for every single logarithmic function is always going to be all real numbers. And every logarithmic function has a vertical asymptote and a vertical asymptote only. All right, make sure that you label those clearly and write your asymptotes as equations of lines.